1, and this was question 16C. So we're being told to evaluate. So this is actually an example of a definite integral. So it has the limits. The higher limit is 3 and the lower limit is 0. So into the integral of the root of 3 plus x over 3 minus x dx. Now this is quite a little bit different because you cannot directly see that this is actually a number. It will also require sign substitution. It's because we don't see any value being squared and we don't see anything like that, and it's because we have everything under the same root. Now when you have such a number, you'll actually have to first rationalize. So rationalizing is going to be the first step. So we're going to rationalize the denominator value. So when you rationalize the denominator value, this is what we end up having. So when rationalize that, because we will actually want to eliminate the root from the numerator, so that we only have it at the denominator. So this is what we end up having. So we'll be left with 3 plus x squared over 9 minus 3x plus 3x minus x squared. So when we solve that, we can actually see that the root of 3 plus x squared, this 2 and this root shall cancel. So at the numerator, we'll no longer have a root. So we'll be left with 3 plus x at the numerator. Now the denominator, we can say at negative 3x plus 3x, these 2 will cancel. Then we'll be left with 9 minus x squared over the root. So we're only left with a root in the denominator. So now, as you can already clearly see, that now we can actually directly use sign substitution. So by sign substitution, before we do that, we can actually first factorize out the 9. So if factorize out the 9, we'll be having a 9 into 1 minus x squared over 9. But remember that the root of a 9, the square root of 9 is actually 3. So the 3 comes out of the root. So inside we'll be left with, actually, 9 here also is 3 squared. So we can actually pull out that power. So we'll have x over 3 squared. And we'll have something like that. So now we can directly use sign substitution. So by sign substitution, we can actually see that the x over 3 shall be equal to sine theta. So x shall be equal to 3 sine theta if we make x the subject. So if we differentiate that, dx theta shall be equal to 3 cos theta. And then if we make dx the subject, dx shall be equal to 3 cos theta d theta. So if we solve for theta, we shall see that theta shall be equal to sine inverse of x over 3, as you can see from right here, if we make theta the subject. So we shall have the integral of 3 plus x over 3 into 1 minus sine squared theta times 3 cos theta d theta. Then if we make x a subject, we can actually see that actually we'll have to eliminate this x here. But we know that the value of x from here, x is actually equal to 3 sine theta. So when we substitute that back in, we'll also have 3 plus 3 sine theta. So now what happens next is you can actually see that this 3 and this 3 cancel, and then the root of this shall be equal to cos theta. Now you can see that this cos theta and this cos theta cancel. So we'll be left the integral of 3 plus 3 sine theta d theta. And then when you integrate that, we have 3 theta plus 3 into negative cos theta. Now everything, because we have limits, they'll have the limits of 3 and 0. So that's going to be very, very key. Now before we substitute in the limits, we'll actually have to first find what cos theta actually represents. So we put everything in terms of x. But let's first solve for this cos theta. Now we know that sine theta is x plus x over 3. So now they know that we can actually put this in a right angle triangle, and we know that sine represents opposite over hypotenuse. So the opposite value must be x and the hypotenuse value must be equal to 3. So now we can find this adjacent part right here. So from Pythagoras theorem, we can set we have s squared plus x squared being equal to 3 squared. So s squared shall be equal to 9 minus x squared, of which s shall be equal to the root of 9 minus x squared. And then therefore our value for the adjacent shall be equal to root of 9 minus x squared. So therefore it means cos theta, which is actually adjacent over hypotenuse, shall be equal to root of 9 minus x squared over 3. And then therefore we can actually substitute that back, and we'll have this. But we remember that theta also is equal to sine inverse of x over 3. So you can actually clearly see it from here, theta is sine inverse of x over 3. So we substitute all those values back, and then we'll have 3 sine inverse of x over 3 minus 3 into this value right there. So now that we have that, we can actually now plug in the limits. So when we plug in the limits, so we're going to have the group where we've plugged in the upper limit and the group where we're going to plug in the lower limit, and then we'll have the difference of those. Now we can already see that 3 over 3 is actually equal to 1. So we have 3 sine inverse of 1. Then we can actually see it from here that this 3 and this 3 cancel. So right inside here we're left with 9 minus 3 squared, which is actually 9 minus 9. So we have 0 over that. So you can actually see that these values here just cancel. So this is actually unnecessary right here because they actually just cancel. Now 3 sine inverse of 0 is the other value, but not sine inverse of 0 is 0. So this is actually also off. But now let's go back here. So now this 3 and this 3 cancel, and then we'll have 9 minus 0, which is actually 9. So we have root of 9, which is actually 3. So we're actually left with the root of 9 right here. But there's this minus sign, so we'll have a minus negative root of root 9 from right here. But remember, root of 9 is actually 3. So, but this negative and this negative also combine and they become a positive. So we have 3 sine inverse of 1 plus 3. Now we know from the knowledge of radians that sine inverse of 1 shall be equal to 1.57. So now if we multiply at 1.57 times this 3 right here, we have 4.71. Then 4.71 plus 3 shall be equal to 7.7124, and this is going to be our final answer. So now just remember that in this case we're going to have to substitute, as we're going to have to put our calculator in radians to actually get this answer right here.